Okay, we're very happy to have Ali Enayat here for what should be our last MOPA seminar of the semester to talk about Tarski's undefinability of truth theorem strikes again. Go ahead, Ali.
Thank you very much, Athar. It's a pleasure after a long hiatus to be able to participate in the MOPA seminar. As you can see, took a title from Star Wars of some 40 years ago. Tarski's theorem has always been a source of fascination for me because it tends to pop up in unexpected places, and somehow when I look back at my education, I never saw it actually officially in any course. You keep seeing different versions of it. So somehow part of the reasons I wanted to give this talk, and thank you to Athar and Raman to accommodate me, was to organize, to be honest with you, my own thoughts about exactly what's happening with the different versions of this undefined view of truth. So my talk in outline will have two parts. The first part is this pedagogical setting the stage, just focusing on Tarski's undefined view of truth in its various formats and different manifestations. I've used the abbreviation TUT for obvious reasons, but I'll be pronouncing it as tut because tut in Persian is a kind of berry which is very sweet, and it's also easier to pronounce tut. So I might be using that abbreviation, although I will try to say the full thing. So there are two sources for this version, which is the latest version that Tarski presented that I know of. They both appeared in 1953. One part was part of this collection of essays collectively written by Mostovsky, Robinson, and Tarski called Undecidable Theories. But each particular piece of this particular book, which is a small book, is actually a little paper and has different versions of the ordering of the authors. So the one I have in mind is called Decidability and Essential Undecidability as part of this book. And the other one is a small abstract. Well, all abstracts are small, but even as far as abstracts go, this is a pretty small abstract by Tarski in the Bulletin of AMS in the same year. I was particularly amused to see this particular abstract because it was Tarski's own wording of his own theorem. So he's really owning this particular version, even though it comes in collaboration, and he acknowledges, of course, the influences of various people, including Robinson and Tarski. In the second part, I'll be talking about how the undefinability of truth joins hands with definability of truth, but in this partial format, to deliver new incompleteness theorems. And this is now more very recent work by Albert Visser and myself. And a preprint is available on arXiv, as you can see on the bottom of the screen. Okay, so here we go. I'll be distinguishing between the semantic form of tut and the syntactic form. The semantic form is basically model theoretic. The syntactic one is, as the name suggests, is just about theories, and there's no mention of models. Before I start, as my abstract has indicated, and in case you had not seen the abstract, I basically make a statement there that one version of the undefinability of truth is very quick and short. You can prove it in one line if you just your line is long enough, maybe on a board, or as you see on my screen, it's going to be 3 lines. It's basically Russell's paradox reformatted. And the other one, which is the syntactic one, takes a bit more effort, but still is far simpler than you would think, having seen the classical presentations of it. So the semantic form, I'm going to have it in the following format. We fix a particular language, and for me, language and signature are the same thing. And I pick a particular model M, which is an L structure. This is the background model. And then we have a mapping of unary L formulas into M. Now, I didn't use the Gödel numbering symbol, the corner symbol, to emphasize that this is just any arbitrary mapping of formulas into the domain of discourse of the model M. So think of it as the code of phi or just hash phi. Now, the semantic form reads as follows. There is no binary formula T of xy in this language O, such that for all unary L formulas, M satisfies for all x T holds of x and the code for phi if and only if phi of x. So basically, the extension of any given formula phi can be found as a cross-section of T. Okay, so in this particular formulation, as you see, the proof is very nice and sweet, having seen Russell's paradox or Cantor's theorem. Suppose not that there is such a formula, and consider the unary formula R of x obtained by just looking at naught of T of xx. Now, just by the way we demanded the formula T to behave, we have condition number 1 based on using R of x instead of phi. And if we let lowercase r over here to be the code for R, now this is a member of M now. Remember, these are mappings of formulas, unary formulas into elements of M. So lowercase r is just a member of capital M, the domain of discourse. Then using the property 1 and the definition of R, which was this R of x as negation of T of xx, we obtain a contradiction because this first equivalence is because of the way T is supposed to behave. The second equivalence is just the way R was defined.
Ali, so
Yes.
can I ask you a question now? Because I
Yes, of course.
about the sources of this form. Have you dug out the earliest mention of it, or like something in print?
Thank you for asking this.
I just want to say I know this argument from Jim. Jim told me once.
Yes,
and
yes.
He formulated in this form that this T would be like what's called a universal set for definable one-dimensional sets, and the formulation would be that the universal set cannot be definable. So, but what is the source for it?
No, I don't have the source for this. And this is for the other one, I have the source, which was the 2 papers that I mentioned. For this one, I, just like yourself, I actually learned this from your own paper in which you mentioned Jim's. So we're going to look at this point. But given the simplicity of this formulation, I would expect this to have been known a long time ago. But it would be nice to know.
Maybe known to everyone. CUNY and Church, they all knew that, I guess.
Yeah, it's the kind of thing that we all know that in retrospect everything looks trivial, but at the same time, it's at some level it's possible this was never formulated because it was just it was in the background.
Right. Because also I sometimes had a problem because when you do it semantically in a sense over a model, then this T also can have parameters as well. So
exactly. Yes.
And
yes.
So maybe Dave knows where it comes from.
Yeah, if any of the listeners and viewers know of a semantic form in the form that I have it here in this negation.
In the CUNY post work on the arithmetic hierarchy, this sort of exact argument comes up over and over. You can't have a universal delta n set, for example.
Yeah, that's true. Yes, with parameters, things shift a bit, right? So in a recursively saturated model, there's a parameter which codes the theory of the model. So that's why the formulation one has to be careful how to word it. So I've just added this line about how the proof is reminiscent of Russell's paradox and of proof of Cantor's theorem on non-existence of a surjection of a set onto power set of x. Okay, so as far as the corollaries of this semantic form, if we use the abbreviation form super n lowercase n for the n-ary L formulae, so n-ary meaning there are exactly n free variables, and if you have an L structure again with a pairing function this time, then we could divide the codes of sentences in the elementary diagram of M as the positive and the negative fragment. So the positive fragment is what you're seeing on the screen, is pretty much the obvious thing. So notice just the way I've written it, everything is now a member of M because hash phi is a member of M, and then we have we have a pairing function, so this is a member of M, and then we apply coding again. So this is now a subset of M, And then, of course, the negative fragment would be just the sentence has to be false. So given this particular splitting of the elementary diagram into the positive and the negative fragment, we can then obtain the general theorem in any L structure with a pairing function. The positive fragment and the negative fragment are definably inseparable in M. There's, in other words, there's no parametrically definable formula, capital D, which contains the positive fragment and excludes the negative fragment. And so in our own experience with models of, let's say, arithmetic, typically these hash phi, the code for phi, is a standard element of the model. It's an element of the model. It's a standard element. And so this would be, so in general, because we have also non-standard formulae, it's obvious that you cannot define the elementary diagram because the standard cut would be definable then. But the question is generally not whether you can define the standard cut, but whether you can separate the false statements from negative, the true statements, which is what this corollary delivers. And then as a corollary to the corollary, we have basically, Gödel's theorem that if you take TA, true arithmetic, to be the theory of the standard model of arithmetic, oh, I see my multiplication has escaped outside the parentheses, so this just go inside here. Then true arithmetic is not arithmetical, and in particular is not axiomatizable by an arithmetical subtheory of itself, such as PA. So this semantic form of Gödel's theorem, then it takes really minimal diagonalization. I mean, if we think of diagonalization as being at work in the formulation I gave, it basically is just that's the lightest possible diagonalization. So this is in contrast with the syntactic form, as we will see, which takes a little more oomph when it comes to getting the job done. So in the syntactic formulation, we still have a language at work that we have fixed.
Sorry, could you just put the last slide up for another?
Absolutely.
It went by quickly when I was.
Sure, yeah, I'll stay.
Corollary, okay, the corollary is right.
So we take, in this case, so this corollary to the corollary, I'm basically going back to this corollary with the model M, and instead of M now, I'm going to use standard model of arithmetic.
Standard model, right.
Yeah,
right.
In the standard model of arithmetic, everything has a name. So this elementary diagram is the same thing as a theory of the model. Everything can be described like every n is.
Oh, I see. That's the point.
Yeah.
If it's non-standard, then there's a difference. Which one has more information? I guess the one, the elementary diagram, right? Because everything.
Yes, the elementary diagram in general has more information. That's right.
Right.
Yeah.
Okay. Thanks.
Yeah. Sure. Okay. So I'll go on, but please do stop me if there are any questions. So in the syntactic formulation, we now have a mapping of natural numbers into closed L terms. So these are basically terms that have no free variables. So the theory should be of a type that it has function symbols or constants to be able to give you a mapping. But if you don't, that's okay, because you could also have definable terms. So you can have a definitional extension of the theory which has still terms and get the job done. But for the purposes of this presentation, which is also Tarski's presentation, the one you're seeing on the screen here, my notation is different from Tarski, but pretty much the presentation is his. We're mapping natural numbers to closed terms. So this, again, I'm using an unfamiliar symbol, this blackboard lowercase n, to emphasize that this need not be the numeral 1 + 1 + 1 n times. It's just some closed term. We also have a one-to-one correspondence. Again, I'm not using the Gödel numbering because it's an arbitrary one-to-one correspondence that you fix ahead of time between formulas of the language and natural numbers. And being a one-to-one correspondence, we have the inverse of it denoted by this map that sends n to phi sub n. So this phi sub n was absent in the previous argument. Only we had the hash of phi. Now, the diagonal function is a function from natural numbers to natural numbers, omega to omega, given by this formula. Given a natural number n, plug in the numeral, well, the numeral in quotes for n into the nth formula. Now you have a sentence, and then take the code of it, which is now a natural number. Now, what does it mean for a function to be definable in the sense of t? This is again Tarski's formulation. A function from omega to omega is t definable if you can find a binary formula phi of xy such that this equivalence, which has a universal quantifier ahead of it, holds for every natural number n. So this phi gives you the graph of the function, and t can verify its functionality. So that's the point of this for all y, that phi of ny holds if and only if y is equal to f of n. So this is basically what it means for a function to be t definable. Similarly, we define a subset of omega to be t definable if there's an L formula psi of x such that for every n in P, t proves psi of the representative for n, and for every n outside of P, t proves the negation. Another formulation of what it means for P to be t definable is to take the characteristic function of P, chi of P, and then use this definition. And then for that, you would need some assumption that the representative for 0 is different from representative from 1. But right now, we don't even have that as one of the assumptions. This map that we have here, n going to lowercase blackboard n, need not even be 1-to-1. It's just some mapping. Of course, in all the interesting applications, it's a 1-to-1 map, and it's often highly computable. But for this formulation, all aspects of computability have been stripped away. So instead of arithmetization, I would like to think of this as basically mapping. I would call it numberization. There is no such word in English, but you're just numberizing everything. There's no arithmetical operations at work anywhere in this formulation. Okay, so here's the syntactic formulation. Version 1, this is again from Tarski. Given a theory T, let V sub T to be the codes of sentences phi such that T proves phi. Assuming T is consistent, then the diagonal function delta that we saw and the set V sub T are not both T definable. Now, we would, in this day and age, write something like if T is consistent and T has the property that the diagonal function is T definable, then V sub T is not definable. But this is Tarski's formulation. Either this, they cannot have both, you can't have your cake and eat it too here, basically, formulation. And it's a nice exercise, actually, to come up with an example, which I'll leave up to you at your spare time, to come up with a counterexample to this theorem where everything is okay except that you've dropped the diagonal function bit of it. So basically, if we just say V sub T is not T definable. Okay. Now the corollary of this theorem is the syntactic formulation we often think about as the undefinability of truth, the syntactic version, which is if T is a consistent theory such that the diagonal function is T definable, then there is no formula theta of x such that for all sentences phi, T proves phi holds if and only if theta holds for the code of phi. So in the usual formulations we see, it would be something like the Gödel number of phi sitting where n is sitting here. But in this formulation, we have a slightly different notation. So having this corollary, then the way it was used in Tarski's work with Robinson and Mustovsky is that it allows you to get fairly quickly incompleteness from undecidability. Because if T is a consistent theory that represents all recursive functions, and your mapping of sentences to numbers is recursive, then V sub t is not recursive. Equivalently, t is undecidable. And if t is undecidable, it has to be incomplete, because a complete theory is decidable. If you have a complete theory and I give you a sentence phi, then you run two parallel computations, one looking for a proof for a sentence and one for its negation, and sooner or later you're going to get one. Hence the jump, or the deductive jump from being not recursive to being incomplete. So it's a very backdoor way of getting a completeness through undecidability. Just as a remark, every theory that interprets Robinson's R, this is a tiny fragment of Peano arithmetic, which is even weaker than Robinson's Q, represents all recursive functions. So the standard textbook way of showing something is undecidable is to interpret Robinson's R into it. Robinson's R is infinitely axiomatizable, but it has very simple set of axioms. And because it's infinitely axiomatizable, even though it's simple, there are infinitely many axioms, there's a slightly easier version of Robinson's R, which is Robinson's Q, which is basically a finitely axiomatizable theory, which just gives you the recursive behavior of plus and times. It's weaker than PA minus, which still can represent all recursive functions. Okay, so the formulation that is going to be used in the theorem that we're going to be seeing today, this new incompleteness phenomena, would be this corollary, this format, that there is no basically truth predicate for sentences, if we kind of take this formulation. Okay. I have written out the proof here. I'm not planning on going over it because of time, but I wrote it out so you would see how it compares with the proof of the other version. It's the kind of thing that I would think all of us all of you in the audience, given just time and patience, you would be able to work it out yourself, given the formulation, because we have all seen all kinds of statements like this in our experience and coursework, etc. But this gives you a good, I would say, quantitative feeling of why the syntactic formulation takes more effort. Still is nowhere as involved as the textbook formulations we see in which often use the Gödel-Carnap fixed point theorem. So the only, in a way, fixed point phenomena is hidden and tucked away in the syntactic formulation of Tut, Tarski's undefinability of truth. Just for historical purposes, I'm just showing you a screenshot.
Actually, sorry, could you comment? Sure. That's sort of what I've been waiting for, is where you are or aren't using diagonalization and fixed points. So could you just say all that again? Because I think that's interesting. So can you say that again more slowly? And and maybe comment on what it is that you don't get, you don't recover for lack of using that, or maybe that's the rest of your talk. I don't know.
No, the rest of the talk actually is going to be just putting the syntactic form to work in working together with the definable form of truth. Going back to
people sort of informally raise this issue. Oh, are you using diagonalization? And of course, that's not even necessarily rigorously formulated. Maybe it's a matter of opinion and aesthetics. But it does seem that using a fixed point theorem versus not is a matter of substance.
Yes. There's certainly the diagonalization involved. I guess it's good to think about maybe the dose of diagonalization and its unexpectedness, maybe, and its naturality versus somehow devilishness. So all of us exposed to Russell's paradox, we become blasé when we see the semantic version of the theorem, because we've just seen this game too many times. But of course, it was a shock to Frege, right? So the semantic form, conceptually, I would say, is just a dressed up version of Russell's paradox, which of course, there's a diagonalization involved in Russell's paradox by forming the Russell set. And in the syntactic formulation, we need to be talking about the diagonal function, which was missing in the semantic formulation. So the diagonal function, let's just look at it again.
Yeah, I want to see that again.
Yeah, it's this function which is from
right.
natural numbers to natural numbers, which plugs in, given a natural number, plugs the representative for n into the nth formula.
Right, and that's what the diagonalization happens. Right, right, and
Yeah.
it's the two different ends and the two different right. That's what I was waiting for, because I saw I
Yes.
saw something like that. You know, the first time you were asking about history, probably in Yek's book, and it went by too quickly, and I think they weren't in two different fonts, and it maybe took me 15 years of seeing things not written that way.
You know, I was thinking today actually that
so that's very nice.
It's probably a good idea to write an expository paper just for, you know, all of us who didn't see this as undergraduates.
Well, I didn't even study logic as an undergraduate, so I mean, even worse.
Well, I'll give you my own quick experience with Gödel's theorem, which was probably as disappointing maybe as can be. I had heard of the Gödel's theorem for some time in the middle of a recursion theory where we're doing all kinds of very nice, fancy stuff. Suddenly the professor says, corollary, Gödel's theorem, and one line. And my mouth dropped because it was suddenly like a whole catastrophe for me of, I would have liked to be given the warning, you know, of where things are going. But yeah, so I make my slides available, and I think that was one of the reasons.
No, please do. I want to go read this. That's very helpful. I'm gratified that you have it in the two different fonts too. I mean, sort of waiting for that when I saw your abstract actually. So,
well, thank you.
Yeah.
Great, Ali. I like it very much. I just have this one on the side remark, because there is also when it comes to semantic proofs, there is Robinson's proof that uses non-standard models. Were you going to say anything about it? No, because
no, actually,
always, because I recently looked at the original paper, and Robinson there is very happy because he has this argument that avoids the diagonalization altogether, although he says, oh well, there is still some paradox that's sort of hidden somewhere that perhaps. But I like that proof very much. Yes.
If I remember correctly, Robinson's proof was for the semantic version, not for the syntactic one.
Right.
And somehow, to be honest, I love Robinson's proof, but I find it disappointing because I think the proof is so simple that it's just overkill. You know, meaning it's nice that we could do that, but somehow it's not going to come up later in my talk. As much as I like,
I don't know this proof. Is it possible to give a brief synopsis, or would that be too much of a digression? I mean, you say it's over really quickly. It's like a one-liner somehow.
No, I'll tell you where it is, because I have the paper right here. So this is Robinson paper with the title on languages which are based on non-standard arithmetic, and it was published in 1963. But if you Google Robinson and on languages which are based on non-standard arithmetic, it's a long paper written in this kind of very nice.
The title already gives me a hint.
Right. And it's very elegant, and he's really very happy, and it's in the introduction.
Roman, am I right in remembering that the gist of Robinson's argument is that if truth were definable in the semantic form, then basically every non-standard model of PA would have to be recursively saturated? That's how I remember it somehow.
Right. The gist of it is that every non-standard model couldn't be simple, couldn't be generated by a single element. So that's what he uses.
Yes.
So it's a little bit less, right?
Yes.
It's a little bit less, but
it's a little bit less because I guess its theory should be coded in the standard system, which we know.
Right. No, essentially, he uses that if you have the truth definition for the standard model, then you will have the truth definition for some finitely generated model, and you use this definition to show by overspill that it's not really finitely generated.
Yes.
But you can still, but from this you can sort of just formulate the argument. The proof would show that the model has to be recursively saturated. Although you're right, then every model would have to be recursively saturated.
That's how,
But those days, that vocabulary did not exist. So that's 1963.
Yes, that's right. Okay. I guess I'll go on just because of time limitations. But,
So that was a digression, maybe unnecessary.
No, digressions are good. So this was Tarski's abstract. So we just kind of see kind of pretty much he's summarizing his theorem in this nice tiny one paragraph. And then his own assessment, let's just look at this together because he clearly was very proud of this. The idea of this reconstruction and the realization of its far-reaching implications is due to Gödel. The present version of this reconstruction is distinguished by its generality and its simplicity. It applies to arbitrary formalized theories and not only to those in which a comprehensive fragment of the arithmetic of natural numbers can be developed. To a large extent, it is independent of the way in which the notion of validity has been defined for a given theory. And in particular, it does not involve the notion of formal proof within this theory. It does not use the apparatus of recursive functions, although this apparatus will play a fundamental role in applications of theorem 1, which is the syntactic form, to the decision problem. And I've just added 2 articles that discuss this issue of Tarski versus Gödel when it comes to definability of truth theorem. As I recall, actually, both of them take a rather negative perspective toward Tarski's originality, but my own point of view is somehow more sympathetic to Tarski. I believe he certainly added some very interesting twists to Gödel's insight. Okay, this is the end of part 1, and now we're about to shift to basically how this very old theorem comes back to help us, solve a rather modern problem that was recently posed. So this modern problem, a quick look at my time, was originates in the question of Stefan Lemp and Dino Roseger. Stefan was visiting Vienna back in the fall, and Roman was there at the same time. And the way this whole thing started was Lemp mentioned the question to Roman, and then Roman mentioned it to me, and then I initially thought I could answer it using the things that I knew. I bounced it off Albert Visser. He's found a little big crack in my argument. There was one part of the argument which couldn't be fixed unless we did something differently. And then together we fixed the argument. And so what you see is now basically the result of the joint effort of Albert and I. Okay, so the theory that the question was formulated about is PA minus, is the finitely axiomatized fragment of PA whose axioms describe the non-negative substructure of discretely ordered rings. So the minus refers to the fact that we have no induction scheme available. It's just ring theoretic, ordered ring theoretic axioms about plus and times and less than. The question is whether there's a consistent completion of this theory that is axiomatizable by a set of sentences of bounded quantifier complexity. So this was the question. So I'm not going to define quantifier complexity, given, you can take different formulations of it, but basically all of us have seen quantifier complexity in our logic courses, so just take that definition at work. Here I've added how this question actually hooks up with the work of Stefan and Dino, with other colleagues, Uri Andrews, David Gonzalez, Hongyu Zhu, in which they established the following theorem. The following are equivalent over a complete first-order theory T. The first statement is that the set of models of T is pi 0 omega complete under wage, I should say, reducibility, i.e. reducibility via continuous functions. And condition number 2, which hooks up with the question, is T does not admit a first-order axiomatization by formulae of bounded quantifier complexity. Their paper is available in arXiv. As you see on the bottom of the screen, I've given the address for it. So this was how this new incompleteness theorem was discovered. So it turns out the answer is no to this question, but along the way one learns, one has to talk about sequential theories. So we're going to start with the background results. Before I give the answer to the question, I'd like to go back to the question and say, if we replace this PA minus by stronger theories, why the answer is negative. And why in the sense of, how long have we known that the answer is negative? And that's why this next page is rather historical of how we got to PA minus from having started with TA, true arithmetic. So for true arithmetic, the fact that the answer to the Lemp-Rosterker question is in the negative if you take T to be true arithmetic really goes back to the arithmetical hierarchy theorem of Kleene and Mostovsky from 1940s. So that's pretty much where the game started back in the 40s, that a TA does not have a bounded axiomatization. And then Rabin in 1961 extended this to PA from true arithmetic, this highly complex theory, to PA, a recursively axiomatized theory. Now, in the PA formulation, a dramatic change has happened. We went from a complete theory, which was TA, to an incomplete theory. Now, Rabin's theorem is actually not just about completions of PA, but about just of theories extending PA. It says no consistent extension of PA in the same language is axiomatized by a set of sigma n sentences. So, so this is in particular implying a negative answer for the Rossiger-Lemp question for PA for complete theories, but this is saying far more than that. It's talking about the fact that PA itself is not axiomatizable by a set of sentences of bounded quantifier complexity. And that's also hereditary. Any extension of P has the same property. It's not just PA itself, but any extension of it. Rabin's result refines an earlier theorem of Ril-Nardzewski from 1952 that states that no consistent extension of PA is finitely axiomatizable. Both of these proofs are actually model theoretic and they use non-standard elements. So what's lovely about this being MOPA, about these two theorems is that you're proving something about theories, but using non-standard models in an essential way. The modern exposition of these results can be found in Kay's book, and I've given the reference for it down here.
Hi, may I interject again?
Yeah.
Right.
Sure.
So 10 minutes ago, when there was
Yes.
there was that very brief discussion of Robinson's non-standard model theoretic proof of, right? And then
Yes.
somehow this does that have any relation to this? Because this is something I actually did read about briefly.
No. This one is in the scheme of things.
The Robinson one was actually taught using non-standard syntax, right? And this is non-standard model. Is that the difference?
No. Actually, Robinson does a lot in that paper. He certainly does talk about non-standard syntax. But if you take away the non-standard syntax, even part, I mean, okay, so there's obviously in any non-standard model, there will be non-standard syntax.
Right. And his title is explicitly
yeah. So basically it
yeah.
kind of it led to.
Whereas I don't think this stuff here, I don't think this used non-standard syntax per se. It was just, you just started out and said, it said, consider a non-standard model, right?
Yes. The non-standard formula somehow implicitly entered the scene, but they're overtly, these results are, I would say, of a different caliber than the Robinson. So basically the first proofs were model theoretic, as I just mentioned here, and then there's another strategy using proof theoretic machinery, cut elimination in particular, partial satisfaction classes, and the second Gödel incompleteness theorem to get the same result. So there are really two different proofs of Rabin's result. And for this other one, I've given the reference in the Hayek-Putlock book. This is then the PA case, and then Montague was able to establish a similar result using this proof theoretic machinery that you see in the first paragraph for a large class of theories that nowadays we call inductive sequential theory. These theories have the power to prove the full scheme of induction over the natural numbers, and also they're able to code sequences. I'll give them a definition of sequential theory in a few minutes, but intuitively, basically, it's a theory that can handle arbitrary sequences, not just pairing. And in this particular setting, again, we have to look at what's the hierarchy at work of quantifier complexity, and you can just use as your measure quantifier alternations depth in the Montague formulation. And then by Montague, not only you have an PA fitting the format of an inductive sequential theory, but also Zermelo set theory, which is a weakening of Zermelo-Frankel because you don't have replacement. Z2, second order arithmetic, and Kelly-Morse theory of sets. So basically, to make a long story short, the question that was posed by Lemp and Rossiger for PA minus, for T equals to PA minus, has a positive answer, sorry, has a negative answer. There is no consistent extension that is complete, that has sentences axiomatized by sentences of bounded quantifier complexity. If the theory is one of these canonical theories that you're seeing on the bottom line, PA, Z, Z2, and KM. Again, notice any extension of these would work also. So ZF fits the bill here. Okay, now we talk about sequential theories. So as I just mentioned earlier, sequential theories accommodate a modicum of coding machinery to handle finite sequences of objects in the domain of discourse. So Gödel used the Chinese remainder theorem to show that PA is sequential. Ježábek, not too long ago, 2012, showed that PA minus is sequential. And Visser showed that Q is not sequential. So sequentiality is a property shared by many theories, but not all. So Q stands out, but PA minus, surprisingly, is sequential, as shown by Ježábek. Actually, Ježábek's proof shows that even a weakening of PA minus is sequential, in which the predecessor function is not necessarily well-defined.
Ali, I know you've said this at some point, but
yeah.
I keep losing track. What is the distinction between PA minus and Q?
Sure. For the purposes of this discussion, PA minus, because it's the axioms of ordered, the positive part of ordered rings. One of the axioms says that x plus y is equal to y plus x. But in Q, we just know that we only have for all x, x plus the successor of y is a successor of x plus y.
I see.
So it's just, you have weaker axioms. And in this theory Q, you can't even prove x plus y is equal to y plus x. So think of Q as just basically a weakening of PA minus that looks in a way too weak. And what was surprising when Q was introduced in the Tarski, Robinson, Mostovsky book was that Q is able to represent all recursive functions. And nowadays, we know that Q also can interpret I delta 0 even. So it can not only interpret PA minus, but it can interpret I delta 0. So it's actually overtly weak because it doesn't even know x plus y is equal to y plus x. But it can define a cut of itself, a definable initial segment, on which I delta 0 holds.
And then R is even weaker, or just
yes. R is even weaker.
So like, what's an example of, is there like an easy example of something in Q that R can't even prove that's like even more blatant than commutativity of addition?
So actually the axiom that I just mentioned, x plus s of y is equal to, so the successor of x, how about this? Successor of x plus y is equal to
inductive clause. The inductive clause.
Yeah. So basically, R is, I would just say R is elementary grade school arithmetic without quantifiers. It just knows, all equations of the form m times n is equal to p if m times n is really equal to p, and the same thing for plus.
Oh, so it doesn't even have like these successor clauses built in explicitly.
Yeah, it's a very local theory, and
it's just a collection of facts about those.
It's a collection of very trivial facts. Exactly. Yeah.
Wow. Now that can't possibly interpret delta
yes.
0, right?
Yes, but no. I mean, R, it cannot interpret. R is not finitely axiomatizable.
Right.
But
it's a
even
collection
R
of
can represent
forms,
all recursive functions. So this is how this is one of those surprises, that you have a very weak looking theory, but it still has a lot of representation power. Yeah. And what's really nice about Q is that Q can encapsulate everything R knows in just finitely many axioms. And so if you want to show something is undecidable, instead of a long proof of checking that R is interpretable, you just check that Q is interpretable, which are just some very nice basic axioms. So is it okay? Can I go on now?
Yes, thank you so much.
Yeah, it was.
Yeah.
I muted myself already. Yeah, that's
Okay,
good.
okay. So this next bullet item is two characterizations of sequentiality. One of them is T sequential if it has a definitional extension to adjunctive set theory. Now, adjunctive set theory, I haven't written the axioms here, but adjunctive set theory is, you can think of it as just baby set theory. It has one axiom which says there's an empty set. There's another axiom which says given any x and y, x union singleton y exists. So you can adjoin a given element to a given set. So that's adjunctive set theory. It doesn't even have the extensionality. And it turns out it's a deep, I would say, bootstrapping theorem that sequentiality is equivalent to having a definitional extension to adjunctive set theory. The original definition due to Putlock of the extension of sequentiality is as follows. I'm putting this definition here because it plays a role in the way things are going to be set up on the next page or on. In this format, you have a particular formula in your theory n of x, which you read as x is a number. Think of a natural number. It picks out a bunch of numbers which behave like natural numbers. There are also formulas providing interpretation of equality and operations of successor, addition, and multiplication for elements satisfying n of x. So we have like a baby model of arithmetic here inside of this model, such that T proves the translations of the axioms of Q when relativized to n of x. So that's finite many axioms. And additionally, there's a formula beta. Remember, Gödel also used a beta symbol for his coding. Beta of xiw, whose intended meaning is that x is the ith element of a sequence w. Now, the axiom for beta says that T should be able to prove is that every sequence can be extended by any given element of the domain of discourse. So basically, we have it. I didn't write the axiom down because that would be not pleasant to the eye. But the idea of one axiom basically saying that sequences can be extended by tacking a given member of the domain of discourse at the end of the sequence.
Okay, sorry to.
Yeah.
Here's yet even another reason why I wanted to come to this talk. Right, so I've been kicking around something I want to do with sequential theories for years, but I don't know. I won't bring it up now in public. But what I'm wondering here, though, I mean, when you say this formula beta of xi, so I'm looking at this and like, if you were to formalize that, right, then this would include the statement that like I actually like, you know, whatever I is a number, that capital N of I holds, right? Right.
Yes,
so,
exactly.
Your X and your I and your W are all in your original range of discourse, yet you're interpreting X as a sort of elementary element and I as a natural number index and W as a sequence. But actually there's just one sort, right? And you've got various bits of syntax there to manage that. Okay.
Yes.
Your spare time, I want to do that for real closed field, for algebraically closed fields, or find a reference where it's been done. And I've been trying to track that down for 25 years. But
no, wait. I think algebraic closed fields don't admit a pairing function. So you
well, no, but I mean, maybe not. But I mean, if it could be expanded.
Oh, I see.
Right. I'd like to somehow have a theory that sort of like has retains as much of the completeness as possible of algebraically closed or real closed fields, yet allows you to talk about finite sequences and linear algebra and so-called elementary proofs. And whether anyhow, that's something that if there's any content to it, it's been done years ago and I've never found it. But I'll talk to you in private.
Okay.
I have a math overflow. Maybe I mentioned this to you last year. I don't know. But
okay, that's fine. Sounds
but
good.
anyway, this is good. This is just all the stuff going around my head. Or I should read this paper of Pudlock.
Yes, in the paper, the axiom is written out. So if you just
so it's a paper of Pudlock called sequential. Because I know I've read there's a paper
actually,
of Hisser,
I would suggest. I mean, you can certainly look at Pudlock's paper, but in the paper of Albert and myself, we repeat the definition, and it's on archive. And
so maybe I did read that paper. Yeah, maybe I did read that paper. Look at that paper at one point a long time ago. Okay.
Okay. Okay.
Yeah.
All right. So, so what can sequential theories do? Well, first of all, they're self-improving. That Q that the numbers are required to satisfy by definition of sequentiality can be self-improved to ideal to zero. And this is thanks to a deep theorem of Alex Wilkie from 1980s that Q can interpret ideal to zero on a cut, meaning on a definable initial segment of itself. So for all intents and purposes, when you think of a sequential theory, think of the numbers of the theory satisfying far more than Q. They can be required to satisfy ideal to zero. And then we have the following result, which was established by Albert Visser in 2 goes. In 1993, he describes a theorem and outlines the proof. In 2019, he tightens all the nuts and bolts and completely gives the highest. I mean, Albert is a very rigorous mathematician when it comes to his expositions, but even for Albert's, I would say, exposition, the 2019 has all the possible details you could ever care to want, and I'm sure it's easily implementable on a proof assistant, for example. Anyway, so this result of Albert refines the work of Putlock from the 1980s. The difference between Albert Visser's and Pavel Putlock's work is that in Pavel Putlock, logical depth was used as the measure of complexity, whereas in Albert's is the depth of quantifier alternation complexity, which is related to the Lamb-Prossergo question. Logical depth is just the length of the longest branch in the formation tree of the formula. So what is this result? It's really about partial satisfaction classes in this setting, but one has to formulate it in a careful way. In the paper, we call it fact F, and so I've also here called it fact F. Suppose T is a sequential theory formulated in a finite language, L, and fix a natural number. Also fix some interpretation of arithmetic in T satisfying I to the 0, which in the first bullet item I said is possible. There's a T provable definable cut I sub n of n. Let's just pause here to see what this means. It means there's a formula in the language of the theory which defines an initial segment closed under plus and times. That's a definable cut portion, and T is able to verify that. Along with the formula sat sub n, so this formula depends on the n that was fixed up here, such that provably in T, sat sub n satisfies Tarski's compositional clauses for sigma n star formulae that happen to be in I sub n, this cut. Now, what is this star doing here? This star is just to indicate that we're talking about quantifier alternation depth as opposed to the usual sigma n hierarchy we see in arithmetic. Now, in PA, these two collapse into each other because of, for example, the MRDP theorem. But in a general theory, these two are distinct, and in this particular context, sigma n doesn't even make sense because we're not in an arithmetical theory. We're in some arbitrary theory which happens to be sequential. So again, to repeat, this is the collection of formulas of the theory whose alternation depth is bounded by n, sigma n star. So this is basically what part A, which is the important fact. From this, it immediately follows that there's a formula of one variable. This one was 2 variables to the satisfaction predicate. This one is of 1 variable, such that probably in T, true sub n is extensional, i.e. it respects the equivalence relation representing equality in the interpretation of numbers. And more importantly, for all models M of T and all sentences in sigma n star, basically this formula true sub n is giving you a truth definition. This looks awfully, if not exactly, like Tarski's truth definition, except it's not required to work for all formulas. It's only working for formulas in sigma n star. We know by Tarski's theorem, we can expect it to work for all formulas. So this is the nice, I would say, I hate to use dialectical, maybe in this case, but I'll use it anyway. So we have a dialectical situation where truth is undefinable, and yet approximations of it are definable, and they come together now to help us, the undefinability and the definability. We need at this point a break, and the break is given by this telegraphic history of definable perio, supposed to be partial truth predicates. This truth predicate that you see here has a long pedigree, and in this commercial break, we're just taking a quick look at how this game started. At what point did it start? In my mind, it started in the 1940s in the work of Turing, Post, Kleene, Mostovsky, whose collective work now we see as the nth jump of zero is sigma n complete. Basically, we have a master code for sigma n properties. Mostovsky in 1952 refined that by showing that PA supports a definable truth predicate for sigma n formulae. Montague extended Mostovsky's work by showing that every inductive sequential theory supports a definable truth predicate for sigma n star formulae. So this is, again, the same star that we saw in the previous page. This is indicating alternation depth. Levy, the set theorist, in 65, showed that ZF supports a definable truth predicate for formulas that are nowadays known as the sigma n formula in the Levy hierarchy. This notation, Levy, is not written by set theorists because when they write sigma n, they mean the Levy hierarchy.
Sorry, again, the star, the alternation, the distinction is what? I know they're the same in the arithmetic case. Is this because you have pairing functions for the one and?
No, just think of it this way. In the arithmetical case, for example, sigma 0 would be all formula with bounded quantifiers.
Yeah.
Which, quantifiers are the form for all x less than y, for example.
Oh, I see. The star here doesn't take any special notice of bounded quantifiers. It's just
no. The sigma n hierarchy doesn't. Meaning, sigma n hierarchy is very specific to either arithmetic or set theory. In arithmetic, it's less than. So for all x less than y, it would be bounded. In set theory,
but in general, you don't have the resources to talk about it.
Yeah, you don't have the way of bounding in a way. Yeah.
Right. Yeah. Okay. So this is just sort of right. This is just plain vanilla quantifier alternation without any exceptional cases.
Exactly. Yes.
Okay.
Yes. Yeah. Okay. So in this progression of definable truth predicates, in 1980, Geifman and Dimitrakopoulos refined Mostovsky's theorem by showing that not only PA, which is Mostovsky, but I delta 0 plus x. X is denoting the statement that the exponential function is total. So this fragment of PA supports a definable truth predicate for sigma n formulae. And Putlock showed in the 1980s and in two different papers. The latter one is the reference that I used, that for sequential theories you have a definable truth predicate for depth n formulae, and then we have Albert's that we just saw in the previous page in two formats, 1994 format and the 2019 format. Okay, let me take a quick look. I see now my time is up.
Right, so, Ali, I was looking at the clock as well.
Yes, yes.
And so you know what I'm going to say.
Yes, you are probably going to propose that I continue this at some point.
Like in 2 weeks?
In 2 weeks? I think I should be able to do it. I just have to check with the powers that be, but
right. But we're coming to the meat of this talk, and it would be a shame to rush it. So Athar, what do you think? What do you think?
That sounds fine to me. So I guess it's up to you, Ali, if you if you want to cover any more today. Or if you want to just kind of wrap up.
Actually, this is, as far as a stopping point, I think this is a good stopping point, except maybe what I could do is just to give you the statement of the theorem that we're going to be doing next time, which is basically this statement.
Sounds good.
That gives a definitive answer to the question that was posed by Lemp and Rossiger, because PA minus was shown to be sequential by Emil Jacek's nice paper. So this theorem shows that no consistent sequential theory can be complete if we know the theory is axiomatized by a set of sigma n star sentences. So just maybe as a way of just closing thought, what's going on in this theorem is that we have no information about how complex is the set of sentences where the complexity is viewed as the complexity of describing the theory, meaning if we just code the sentences by natural numbers, we don't know how complex is this set of codes of natural numbers. So the theory itself, this set of axioms, could be highly non-computable and highly non-arithmetical. What we do know is that the axioms are of bounded complexity. So this is where it's different from the usual formulations we see in incompleteness. Usually incompleteness refers to, for example, RE theories or arithmetical theories. But here, the incompleteness is referring to the complexity of the sentences that are required to axiomatize the theory. And okay, yeah, when it comes to, I guess, the continuation of the talk, let me just say that tentatively, I'm pleased to continue in 2 weeks. I just have to check with the schedule of my commitments, and I'll as soon as I fix that, I'll communicate that to Atar and Roman, and we can take it from there. Yeah.
Sure, and you know, we're also at the point where we can kind of be flexible in terms of what works best for you. I think because I'm you know my teaching duties are over for the semester, so you know I think we can work out a day that works best for you.
Okay.
Whatever you like.
So that sounds good then. Then that's going to make it even easier than to come up with a mutually acceptable schedule. Yeah.
Okay, so let's thank our speaker.
Thank you.
And please post the slides so I can be prepared in 2 weeks.
Actually,
or maybe not. If it's the same, you can hold it as you like. I mean, but
no. I'm actually very happy to post the slides because if for those of you who might want to see it before, then
I want to actually read your proof and look at the file.
I'll send my slides to Atar, and then he can just post it. Yeah.
Sure.
In the handout version. Yeah.
I want to thank you for mentioning some of Montague's work, because Montague did all this meticulous, paid all this meticulous attention to how details of syntax and how you could do set theory and things in arithmetic. And it was very, very important, sort of liberating a body of work.
Thank you, Ken, for that comment, because I've also long admired his contributions. And I somehow feel that his name is not sufficiently known in the foundational circles. And it's nice to advertise his this early work of his. I mean, I know he passed away not too long after these results. It was in mid-60s, or was it 70s? I don't remember right now.
But also, is it true that I have some vague recollection from the Bergman's book that he and Tarski didn't get along very well? Or I'm completely confusing it. Ken, do you remember?
No,
so I'm getting things wrong then.
Well, I know from that book that Scott and Tarski had this big feud, right? I mean, falling out.
That I also know, but I thought there was something about Montague, some personality conflict, but maybe I'm making it up.
I mean, the funniest part in that book which involved Tarski, Montague, and Scott, is how the three of them in Berkeley, when Tarski was teaching the set theory class, were kind of competing with each other. And the funniest part was Tarski competing with the two of them. I mean, you could see the students competing with each other, but there was this kind of playground attitude, when it came to that class, apparently, of who could do what without the axiom of choice and using the minimal number of axioms on the spot.
Any other questions or historical comments? Okay, I will follow up with Ali about next steps offline, and we'll get in touch with everyone in the next coming weeks.
Sounds good. Thank you.
All right.
Thank you, Ali.
Thank you, Ali.
Thank you.